All right, I'm going to get started. I'm going to record another session. This time I am going to try to actually implement alpha beta pruning. So last time I kind of implemented a fake version, and I can talk about what the difference between the fake version and the real version is. It took me a while to work that out, and I'll explain it. And let's see. So I can just go over some minor changes I've made in the code. It's between videos. So, whoops, here we go. So yeah, and we'll try to get it so that the game is actually, so the AI is actually fast enough to. I haven't been able to get it to run at like game speed up to depth 4, and depth 4 in the way that I've been encoding it is 2 moves, right? So it's like going from, it's considering your move, then the opponent's move, then your move, then the opponent's move. That would be four levels deep, and that's not that far. And so I think previously I was thinking, oh, depth 3 is that really good because looking 3 moves ahead is like really impressive for a human, especially an amateur player looking 3 moves ahead. That's really quite good. But that's usually thinking like 3 of your own moves ahead. So that's really like, that would really be like 6 moves. In chess programming, I guess people call these plies. I don't really like that terminology because it's so jargony. But yeah, so just how many turns are you looking ahead? So it's I guess in chess notation, sometimes they write it as move 1, and the move number is actually the move, how many moves any one player has made. So like move 2 for you that is actually move 3 in the game. But okay, let me hide this stuff. This is, I guess I canceled a run previously. Okay, so here's the changes. I'll just go in order of the file that I've been working in. I can move this aside. So I changed some of this stuff, like you can see the blue marking here on the side. That's things that have changed in the Git repository. Actually, let me show you the Git repository. I haven't shown this. I posted a link finally on the YouTube descriptions, but yeah, this is the Git repository. So it's a fork of the Lichess bot software created by a Lichess developer. This Shail Choksi, and yeah, it's a fork, and so pretty much all my work has been in this new file I created called custom engine. I made a couple of changes to engine wrapper just to make it so that it goes to the custom engine. You can see engine wrapper this is all just the pre-built code, but I added this stuff following the instructions on how to use a custom engine, or homemade engine rather. And so then most of my work is in this one, custom engine, which is what we've been looking at. Actually, oh yeah, so I have a configuration file that has like my API key, and I did not want that uploaded, which is good. It's not uploaded. So it's a copy of this default config file where I modified it. But okay, let's get to the code again. While I have this open, I'll open up a Python chess. This documentation keeps coming up as important. I will also open up Lichess. I think I'm logged in as my bot. Yeah, so when you log in as a bot, you get this little icon here. So I'm logged in as BirdBot. You can see a bunch of games that I've played or that I've had the bot play and played against myself, my own personal account. It is not a good. The bot is this is not our game, but the bot has been playing pretty poorly. It does not win very often. It wins when I forfeit because I'm bored, but most of the time it doesn't win. It can beat Stockfish level 1, but it's really slow. Sorry, my bot is really slow. But yeah, okay, let's check it out. So, all right, so here's what I've changed. So, okay, what I was saying is this blue marking here and green also along here indicates it's something that's changed in the repository. So this is the version control interface in PyCharm. So I changed these. These used to say, actually I can hover and show you what it used to say. So it used to be that I had like these character indicators for the different pieces, which was not the most elegant way to do it because the Python chess library already has special symbols for the different pieces. So I switched to using that. So rather than converting from the piece type to a symbol and then comparing the symbols, I'm now just directly comparing the piece types. And I don't know what let's see, we can actually peek under the hood and see how they're representing these. They're numbers. yeah. So they're integers, but this is the nice way to do it, right? This way, if they change how they're represented, nothing breaks on my side. And let's see other changes here. So here's where I call that piece value stuff. I was looking at this when I was changing this. I started to become very uncertain on how to spell piece, but apparently is correct. But if you stare at it long enough, it starts to look really weird. I slightly modified the space score to be 1/64 because I realized, I don't know why I thought 1/32 would be okay, but since the number of squares you could possibly ever attack or be attacked on is 64, I figured we want to keep it below 1 so that space is never worth more than a pawn. There might be a reason we might want to change that in the future, but I want if we ever use the improved score, which I do, I think this version right now does use the improved score. I want it to be I want it to favor material for now over space. This I don't know if I did this between streams. I think I did. So I just commented this out. I don't want to do this hanging piece stuff because that's kind of look ahead, and so I don't want to mix two things up. Okay, so here's some code I built to handle configuration. So this way I can turn off pruning, caching. I added sorting and to set the maximum depth. So I figured that those are things that I want to be able to change programmatically, and rather than changing the code or commenting out parts of the code and putting stuff in, I just set it up so that this is an object that the scoring function will get as input and decide whether to do these things based on. So this is using the Python name tuple interface. It's not an interface, sorry. It's a factory which creates a new class. So the config is actually a class. It's pretty interesting stuff. I don't know how interesting it is. It's kind of interesting. So this is our minimax function. It no longer takes in maximum depth because the maximum depth is part of the config object now. It takes in a cache object, which this is not ideal, but I have it set to take as empty tuple as the cache. I gotta fix that. That's not ideal. If you put in the cache is a dictionary, and if you put in an empty dictionary, Python gives you a warning. So I guess this is no warning, but it's not good, because it expects all my code expects it to be a dictionary. So really, maybe I should just make this be required. Yeah. I'm hesitant to do that. I'll leave it as is. I'll fix it later. Okay, so code. Okay, so here I set this to be improved score. I think I'm 2 commits ahead, which is why this was different from last stream. This was material count before. Now it's set it to improved score, which is material count plus it's space tiebreaker. And all right, so here's where I did something interesting. I create a list of children positions, and I generate those children positions in this for loop. And in fact, I'll just comment this while I go. So generate children positions from legal moves. So this loop here creates all the candidate positions, and what it puts it into the children list as a tuple that contains a score and the board and the move that generated it. The reason I do this is because we want to be able to sort the positions by some score. Ideally, it should be some cheap score that's inexpensive to compute, and then we can use that to determine which moves to look at first when we do alpha beta pruning. So I did that. I forget, did I do that yesterday? I don't know. I did it recently, just when I was taking a break. So now this is the main loop, and this looks at the children sorted. So here I'm sorting it by the first value in the tuple. So I'm using that's accessing the first value in the tuple, and it's sorting. Python used to allow you to just sort this, and it would automatically sort by the first value, but for some reason that wasn't working for me. So here's the more precise way to do it. So you explicitly say that the sort key will be the first entry or the 0th entry. And I want reverse to be true because I wanted to sort in decreasing order. Okay, and then here's the reasoning with the configuration. So if the configuration is set to cache, then you'll do this caching stuff. And there's all this stuff happening, which is caching. It's slightly improved from before. I'll go over the differences. I realized the fen encoding it includes the move count, or I forget what they called. I think it's called the move clock or something. Whatever it is, it's whichever move number it is in the game, and that actually means that if you visit a position at different points in the game, it'll register as a different fen, and that's not really what I want. I want, if you repeat a move or repeat a position, I want it to count as the same one, just based on where the pieces are placed. You should also consider things like castling rights and en passant situations, but those are encoded in all those characters before the last four. So the last four characters encode the counts of the moves, and so I just chop those off now. I don't want to be indexing by those. So I'm just looking up the piece positions essentially, and now and then this code here is a little clunky. I'm getting the cached value from the cache if it exists. Otherwise, I just get 0 and 0. And the reasoning here, I set a new depth, which is what the let's see, what is this? Let me just comment this while it goes so that it's all here. So new depth is compute the depth of score estimate I'm just going to say depth of score estimate if we compute it. So what this is checking is this if statement here is if we would get a deeper estimate than what is in the cache. So if we would get a deeper estimate than what's in the cache, then we'll actually go ahead and compute the minimax score for this current position. But if not, then if we would get an equally good estimate, which would be the same, or a worse estimate, then we just use the cache value. So that's the caching logic. And then this is the if you don't cache. So there's a little bit of repeat code here. So it might be helpful for me to figure out how to remove this, because this is a long function call and it's written exactly twice, and so that's an opportunity for bugs. But for now, it's okay. And then here's the other configuration part. So if the prune option is on, then if the score is greater than the cutoff, then we'll return immediately without recursing. And so I'm doing something, this idea where I return the negative score, the negative best score. That's a little bit confusing. In both cases, I do that. I always do that. I always return the negative best score. The reason I do that is because what this minimax function is trying to do is it's estimating the score of the position. The score of the position. Oh wait, how do I say this? It's the score that can result from your opponent's best move. Right, so it's your score considering what the opponent will do to maximize the opponent's score. So the opponent's trying to maximize its score, but because of the way the material count works, it's just the opponent's score is a negation of our score. So this is actually, I was looking this up. This is actually called the negamax formulation, like negative max, and it's okay. I didn't realize it was called that when I did it, but that's all right. It's just another way of writing down minimax with a little bit. I think it's a little bit nicer because you avoid, like, if it's the min player, if it's the max player, you have, if you write minimax the traditional way, you have to decide whether you're the max player or the min player. In this case, you're essentially always the max player, but your contract is that you'll return your negative score. So this does have this has implications about the alpha beta pruning implementation as well. So let me think. Let me show you the rest of the changes before I get to that though. So here I think the only change here is I broke this into 2 lines. So ignore that. Ignore that change. Here, the main function here, I created a main function to just test things. I might have done this already in the previous stream, I forget, but basically the main function, the change I made here is I added a bunch of configurations, and we basically loop through all the configurations and gather statistics on, let's do, we gather a bunch of statistics on what, how long it takes. So I can run this and show you what happens. So this is the current form. It's getting a current position. It's using these configurations where it's pruning. It's either pruning, caching, or sorting. There should be 8 possible combinations of these binary flags, but sorting does nothing if you're not pruning. So I only have sorting on when pruning is on. But yeah, so I'm gonna run this, and then we'll talk about how I want to change the pruning. Let me think, is there anything I'll need to go over? I think I just want to check the defaults. So I set the default values to true, and 4. 4 is quite, let's do 3. So we're going to depth 3, which is not very deep, but that's like where we can get pretty fast responses. It's still not even that fast, you'll see. So this is depth 3 from this position, which was this was a puzzle position that I'll plug it into an analysis board. Analysis board. Can I just type it in here? Yeah. Wait. Is this right? Oh yeah, this is right. It's just backwards. It's upside down. It's Black's turn, right? I think. Does this tell me whose turn it is? Oh, it's White's turn? Wait a second. Well, something weird happened. I thought it's Black's turn because this is supposed to be checkmate. Or mate in 2. It's supposed to be... what am I missing here? Oh, I didn't... Okay, here we go. I didn't copy the whole thing. Yeah, okay, this code right here is whose turn it is. Yeah, here we go. Okay, so yeah, so now it's Black's turn. And so the correct move, again, just from the last stream, is supposed to be like this. You sacrifice the rook, and then you get a checkmate. So that's the... Oh. Yeah, hi Kiwi. So yeah, this is Python, and we're trying to program a chess AI. And a lot of what I'm building is using this Python chess API, and the lichess API. And so I'm not really, I haven't, a lot of this stuff is, already built for me, but I'm trying to do the reasoning of how to decide what move to make next. But so, and today's task is just to make it faster than what it was doing. Cool, that's great. Yeah, this is a thing that I would teach an introduction to AI. So basically, just think about, like, if you know chess, or even, it's not even having to know chess, just know games where you take turns making moves. The reasoning that we're going to try to do kind of applies to any game where you take turns making moves and where you can see the whole position. You see all information. So they call these complete information games. Okay, so what I was showing you is, okay, I guess I did too many things at once. So I ran this code, and what it's doing, it's just measuring the speed of all these moves, of all these computations. And without the pruning trick, without the caching trick, without the sorting, it takes 16 seconds to calculate the move. It gets the right move. This is the right move, by the way. And then if you turn on caching, it takes 13 seconds. So there's a small savings. And the caching, basically all it does is if it sees a position that it previously saw, it'll just look up the score rather than having to try to compute it. And it computes the score both that minimax function, which I'll look at again. And let's see. So then if you turn on pruning, you get to 8 seconds. And if you turn on pruning and caching, you get to 9 seconds. And if you turn on pruning with no caching with sorting, you get 5 seconds. So it's even faster. And then you get a slight slowdown with all three on. There's some overhead. So each of these is like a trick to speed things up, but they require a little bit extra computation. So sometimes they make it a little bit slower. But you can also look at like how many positions we had to evaluate. That keeps shrinking as you add more of these tricks. So it's hard to tell when we get to more complicated positions. Will these pay off, or will it continue slightly slowing things down? That'll be part of the job here, right? That's the engineering task. Is we can come up with cool algorithms that'll speed things up, but sometimes they don't. Sometimes in practice, they don't actually speed things up the way we expect them to. All right, so let's talk about this pruning trick. So overall, what Minimax does is it tries to figure out what's my best move, assuming that the opponent will make the opponent's best move. Yeah, Kiwi, we'll get to this. There's definitely a lot of really interesting developments in artificial intelligence, and I'm doing like the basic stuff. So this would probably go back to like I want to say like the 1980s is when the stuff that I'm talking about was beginning to become perfected. It's certainly before Deep Blue, so I'm talking like really historical stuff, right? Deep Blue, wait, not Deep Blue, sorry. What was the name of it? IBM's AI that beat Kasparov. I'm talking about before that, like that. So we're talking simple AI. Yeah, the more advanced stuff, using neural networks is dominating. That's AlphaZero, Lila. Lila is the sort of open source version of that. It uses neural networks to do a lot of the stuff that I'm trying to do by direct in this code, and it's revolutionary, right? But we'll get to it, and I would like to do that later, maybe this summer, to start doing some actual machine learning, where the machine learning is going to look at chess and just try to learn how to be good at chess, right? Rather than us programming that, like right now we're telling the computer that this is a game where I take a turn, the opponent takes a turn, and then I take another turn, and at some point you win. That's a lot of information, but and we know all the rules and we know ideas about like that certain pieces are worth certain amounts. Like we know that a pawn is worth 1, a bishop's worth 3. Like I'm putting all that into the computer, but what AlphaZero does and what Google does, the thing that you're talking about, it doesn't even know that a pawn is worth 1. It doesn't know that a rook is worth 5. All it knows is I made these moves and it went, and eventually I won. So from that, it learned its own values for all the pieces, all the types of positions you might consider, and that's why it does stuff that's so surprising that has really changed chess, right? So like at the top levels, people are learning from AlphaZero to sort of rethink how we used to think about what pieces are worth in different situations. Anyway, I'm gonna continue on with this code because I'm trying to record this video for YouTube. But yeah, for a quick answer to your question. Is knowing a good low-level language. So low-level means a couple different things to different people. So low-level, in what I usually hear, it means like it's actually like a really complicated language that like is closer to the hardware. Like assembly code might be considered low-level. In general, when you're learning a new concept, a high-level language is a little bit more helpful because it lets you not have to worry about like fine details. Like low-level languages, you're often dealing with like memory locations and input and output and things like that. Whereas with high-level language, you can just learn about the concepts or reason about the concepts. So we're using Python here, so it's considered a high-level language. So when I do stuff like, let's see, what's an example of a high-level language situation? I mean, certainly everything I'm doing where I'm looking at like a board, I'm getting a chessboard and I'm pushing a move onto the chessboard. That's a high-level concept because it's dealing with this abstraction of a chessboard, and it already knows what it means to make a move on the chessboard. In a low-level language, you don't get that. In a low-level language, you have to kind of say, all right, a chessboard has to be represented by 64 squares, and the squares have to have a bunch of pieces, and so then you have to you program each of those little pieces or little parts of the reasoning. So high level languages are nicer for learning new concepts, but eventually, if you want to get good at computer science, you should learn all types of languages, and the more you learn, the faster you learn the next one. Yeah, C is great. C's low level languages are also faster because you get a lot more fine grained control. Right. So, for example, the way that I'm calculating stuff with these chessboards, I don't really have any control over how fast they're being computed. So that's part of the reason my bot is so slow. It's because I'm not using a low level language. Like if I were competing in a time controlled tournament where I was supposed to build an AI to make moves fast, I would not be able to. Using Python would be a bad idea. Like you'd probably want to build it in C for that reason. Okay, so let's talk about this pruning. So we're always trying to figure out what's the best move that I can make, considering that my opponent will make another move to refute what I do. And what I did last time was I came up with this idea, the simplified form, which is that I have a cutoff, which is the cutoff is the score of the best move that I've seen so far, that I pass down to the next recursive call of minimax. And the reasoning for that is that when the opponent finds a move that's better than my best move, then I can just stop I can stop considering that alternate move. So let me be more precise. So if I make a move, if I advance a pawn, and that gives me a score of 0, right? So 0 is the score that I estimated for that pawn. Then I consider a second move, a different move. Rather than advancing the pawn, I want to develop my knight. So I move my knight out. And then my opponent immediately takes the knight for free because for some reason that hangs the knight. If that happens, then I already know that I shouldn't bother considering what else will happen if I move that knight out, because already that knight led to a bad situation for me that is worse than the other option I had, which was to advance my pawn. Right. So that's the reasoning. So this cutoff idea captures that, but what it doesn't capture is that suppose the opponent discovers a better move a few moves down, right? Not right away, not in the first move, but a few moves down. That's where the classical alpha beta algorithm did something smarter. It rather than, I guess the reasoning what I wrote down with this cutoff algorithm, it's basically saying, if I from the perspective of the current minimax player, if I find a move that's better for me than my parent or my opponent, if I find a move that's better for me than an alternate move my opponent had on the previous turn, then I should just stop searching and let the opponent make the other move. And what alpha beta pruning says is that this can be for any previous move for the opponent, not just the one directly previous, but any older move. So in the tree, in computer science language, we would call this an ancestor, right? Rather than talking about the parent of the current node, we would talk about an ancestor of the current node. So it's like further up in the tree. So to accomplish this, we have to keep track of a min and a max, and so it's a little funky. I'm gonna try to code it. It's really hard. It's hard to just explain it quickly and also code it. I also have limited time. I was hoping to do an hour of coding here because I have one of the things that's funny is that, well, not funny, but when I'm live streaming as a break from my other responsibilities, but that also, when I owe other people work that I told them I was going to do, they see that I'm live streaming, and so yeah, I'll get my work to you, coworkers and bosses. Okay. So I'm going to add another term here. So rather than just having a cutoff that's an infinity value, I'm going to also have I thought of a good name for this earlier. Let me make this multi-line because it's a little bit hard to read. But let's see. So one is a cutoff that's a lower bound. So alpha beta pruning, it's an old algorithm. It was named by somebody. I actually don't know the history. You can look at chess programming wikis and you can find it. but the alpha term is the lower bound, the beta term is the upper bound. It's like, but I don't like that naming because alpha and beta, like what is that doesn't tell you whether it's upper or lower. I think maybe better is if I just call it lower and upper. So I'm going to say this is I can rename this. Where's a refactor? Refactor, rename. Let's call it lower. I'll just call it lower and upper. All right, so I'm setting them to be as loose as possible. Although this situation is impossible, right? You can't have a lower bound be infinity and upper bound be up negative infinity. Maybe I'm supposed to set this to minus and positive. Okay, so where does this come up? This comes up in here. So now I have that if the score is greater than lower, I was going to prune. Originally I pruned here where we were saying that if the score is less than, this is so challenging. This is definitely challenging, so bear with me. The logic is tricky. So this is doing recursion, and it's dealing with reasoning about recursion at multiple levels. I'm trying to resist the urge to just like look it up, right? So there's code out there, not just, there's pseudocode out there that describes exactly what the logic is here, but I want to do it in a way that I actually understand it. So the intuition is that the lower bound is I have to think about this. Because before what I had was working. So let me just think about this. So this is the version I had that was working. And then the upper bound, I'm just going to have it be negative infinity. So what I had before was that this lower term was, I used it here. I used it as that if we discover a move that's better than this lower term, then we should immediately return and say, don't bother searching anymore because we found a better move than what you previously had. Better move for me, right? Better move for me than what my opponent previously had. So that I don't think should change. What I think should change is that when we pass down the cutoff, we used to pass down the best score as a cutoff. So this should actually be the upper bound. So I think we pass in, this is going to get messed up. So this is all part of the coding process, especially with complicated code. I think we pass in the upper bound and the lower bound as the new upper bound. So we sort of flip the roles of the different bounds. And the upper bound is going to get the upper bound will be updated to be the best score we've seen so far, or the upper bound. I think this is correct. But we have to walk through it and make sure it's correct. So, okay, I've written down some stuff. It seems like nonsense. Let's see if it makes any sense, or see if we can make sense of it and verify it. So the logic here is that, our we're going to assume that lower always means ancestor score. I'm going to rename this also. Let's call this. See, again, the lower and upper bound reasoning of alpha beta pruning is just not intuitive. So to me, I think it's actually helpful to think of it as opponent best. Okay, so what that means is that that's the best score that the opponent has seen. And then this is going to be my best. Oh shoot, I should rename that. I should do, so it's Shift F6. So my best. All right, so here's the logic. I'm just changing the naming of these so that they make more sense intuitively. So opponent best is what is the score of the best move my opponent has already available, right? The best move that the opponent already knows about. And the reasoning is that if we discover that we can make a move that makes the score worse for the opponent than the opponent best, then we should just stop searching this for this. We should stop considering this move or this current position, because we'll never get to it. The opponent will play a different move, so there's no point of even considering this anymore. On the other hand, my best, this one is to keep track of what the best one, it's the best move. Sorry, it's the score of the best move that I know about my player throughout the rest of the search, which means that as soon as I see, I guess it means that when I run the minimax call on the next move, I will ask it to stop searching if it finds a move better than my best move. By the way, Kiwi, I just saw the comment you made about, you heard that tens of Python lines can be just as fast as a few lines of C. That's a reasonable estimate, but lines of code is also not the best way to estimate how much something, how long something is. But yeah, I think it's a pretty good rule of thumb, right? So that's what happens when you have high-level languages. High-level languages do a lot of work under the hood, like they hide away a lot of the work, whereas C code is just like manipulating computer memory. So it's like doing something really close to the hardware. Yeah. Okay. Every single time I say that word, I have my Amazon Alexa set to respond to the computer word, and so if I say that word, it responds to me. Okay. So, all right. So let's think about the reasoning here. Is this what I want? New depth. Okay. So here, this is just caching. So this is the pruning stuff. So whenever I pass in minimax score, whenever I call minimax score, I pass in my best as the cutoff. I pass in the opponent best. So should I be negating it every time? That's the one thing I'm not sure about. I think I should be negating it every time, because essentially every single time I call minimax, I'm switching the role, right? It goes from the white players to the black player, and back and forth, and so it should be just negating the score each time. So this kind of preserve. I mean, it's a little bit messy, but it preserves the fact that we're always going to have the score written from the perspective of the current player. So I kind of think this is correct. Okay, so I don't know if it's correct. This part's correct. Now this part, okay. This part is that we're keeping track of the best score we've seen so far. I guess that looks correct. So we're trying to find the better score. My best. I don't know. My best also is not really so totally obvious what it is, but opponent best, my best. All right, fine. And then we prune if we're better than the opponent best. I think that's correct. Is it, or should I be comparing? Let's see, score. Yeah, I think that's correct. Okay, so we can try it. The last thing I want to check before we try it is this infinity, the initialization. By default, I set opponent best to infinity, which means that we will never prune. We're never going to be better than infinity. And I set my best to negative infinity. I think that's okay. I don't know. Let's try it. Okay, just while we have it open, I wish I had done this earlier, but I can actually just copy what we had. So this was the result I had before I made all these changes. So I'm going to make a new file. Oops. New. I'm just going to call it notes.txt, and I'm not going to put it in the Git repository. All right, so this is the notes from the run. I'm gonna write down, oops, that this was, I'm just gonna write this run was before I changed to alpha beta pruning, only using cutoff. You know what I wish I had done, like the correct way to do what I just did was I should have committed what I had into the Git repository, which would have saved it, and then anything I did I could undo. But now it's too late. So that's not good programming practice, but it should be okay. So I'm going to run this and see if it works. Okay, so this is with all the speed up tricks off. It should still take like 15 seconds, which is what it used to take. Okay, yeah, 14 seconds, same. All right, so now this is with caching on, so that shouldn't change. The behavior should not change. It did get the right position, the right move again. The number of positions it saw, let's see if that was the same as, hold on. 12 seconds, it seems about right. All right, so this is the first time we're doing pruning, so this is the real test. Will it get the same move? Oh, what? I think it was a lot. It wasn't a lot faster. It was similar speed. But I think this is a key number, right? This is the number of positions that it fully evaluates. And if that number goes down, then usually that means it's going to be a lot faster. So with sorting, no, this is not with sorting. This is with caching and pruning. It was 8 seconds. With caching, with no caching and pruning, pruning with sorting, we only had 7,500 positions. That's quite good, although I think that's similar to what we had before. Then with sorting, we got 6,500, and it was slightly slower, so there's some overhead. So what we've done here is it gave the right output, but it's not clear if it did the right thing, and it could have done the wrong thing and gotten the right output. So we don't have a really good test right now, but at least it didn't, if it gave us the wrong move, then we would know it did the wrong thing. But for now, it looks like it might be working, but it's such a complicated recursion. The logic is hard to keep track of. It's not fully tested, right? This is just, there could be bugs. The test, I think the real test though is, I guess I can kind of hack this. There's no great way to do this. Well, okay, here's what we'll do. Let's compare these. So I'm going to copy this and look at our notes. So this is with first version of, I'll call it A/B pruning. And let's full screen this. So this is our old version, right? And I just want to, this thing keeps printing out my directory structure, which is fine. You can see it, but I don't really want to advertise my directory structure on the internet because I don't know, maybe it could be hacked somehow. So there was a slight speed up on this, but that doesn't make any sense because there was no difference. That was just random difference. But just to check to make sure everything's working okay, we had 37,755. Yeah, it's at 37,755. So that should be the same. This shouldn't have changed. We didn't because pruning is off. All the code I just did was about pruning. Someone says that I can use iterative tools for the product of true falses. I'll check that in a sec. 1 sec. So 22,000, good. All right. So now this is the final one. Not the final one. This is the one where we the important one where we turn on pruning. So this should be different because it's a different pruning algorithm. So we had 19,000 and oops, we're looking for true. Wait, true. Which one was it? Yeah, this one. We want true, false, false. So this is just pruning without caching or sorting. So true, false, false, true, false, false. No difference. Okay, that's not a good sign. So it's possible my logic didn't change anything. In fact, that specifically tells us that my logic didn't do anything. So there's two possibilities. Either there's a bug and my logic is wrong and it didn't actually do anything, or it's not deep enough for it to matter, right? Because we're only doing 3 moves deep. So, by the way, I fixed the counting of the depth. I think in the previous stream the counting was off by 1, but now it is actually 3 moves. So with 3 moves, we're not going to prune unless, I mean, the pruning will, the alpha beta pruning only affects things deeper. Yeah, I don't know. I don't know if I believe that. I think it's probably just a bug. So there's probably a bug, but we will check that now. But this is a good indicator that we got the same number of positions. The number of times that we pruned, I think, is the same. 949, yeah. Same pruning. Okay. So that's discouraging, but good that we caught it. Okay. Yes. So SGK, I see that. I don't want to. So I mentioned earlier. There's something funny about this. These true or false flags. Pruning and sorting. Doing sorting without pruning doesn't make any sense. So I just want to leave that out of the tests. So I just set it this way so I can manually turn some of them on and off. But yeah, for sure this is ugly. But it's okay for now. Yeah, itertools allows you to do something more elegant if you want to try all of the possible true falses. You can even see like another ugly thing is like this is not in binary sort or binary order, right? Because like normally you'd have these flags changing if you wanted to do it in the proper binary order. But yeah, it's because the sorting is a heuristic to make the pruning better. So if you sort by itself, it doesn't actually do anything. Okay, so let's think about this. So how the heck is this still pruning, but just not pruning any different than when I had when I only had a cutoff? So previously I was only essentially using opponent best. And this again is what I mentioned this before as well. This repeat code is inviting a bug because I'm calling it twice exactly the same, and it's a long function call. So if I change it one place, I have to be careful not to. I have to manually change it somewhere else, and it's definitely gonna be a bug at some point. But for now, they're identical. All right, so this is the pruning process. So if we find a score that's better than the opponent best, then we stop searching. That's the right logic. But now we have to think about, are we passing down the ancestor's best score correctly? So the way that works is that we pass in this kind of, so each time we call minimax, we're saying the minimax reasoning has to think of my best as its opponent's best, which makes sense because we're calling it for our opponent's move, and then its best is now what we used to call the opponent's best, and then we negate it because we're changing the who's min and who's max. I don't know. It sounds right. Yeah, it sounds right. One thing I could, this is so annoying. I wish I'd see the thing I set up here is I was able to like test turning on and off changes I've made. But now that I've changed pruning in place, which is just bad form, it's tricky for me to undo it because I didn't commit before I made this change. Well, here's what I can test. I want to do a formal test, but I can do an informal test. The informal test was that when I was doing depth 4, this bot was super slow. So let's see if it feels super slow when I do depth 4. In fact, I think I remember... It might have been, okay, let's just try running it. So this is going to take forever. I'm going to do Well, I'll just run it. So this, I set the default to 4. In fact, I could do it here, but yeah, let's try it. I don't know. This is like that thing that you fall into when you write code and you you discover an error, and then you stare at the code long enough and you try to figure out what the error was, and then you just try running it again because maybe the error's gone. but I don't think it's gone. I something must be wrong, right? Something must be wrong in my code, because it should be different. But yeah, like one possibility is that the reasoning about your ancestor's best move doesn't really kick in until you get deeper into the search tree. So if that's the case, then this is what we'll see. We'll see something. So this is like without pruning is super slow. I'm not even gonna let it run. So this is where I'm gonna do some hacks. I'm just gonna turn on pruning. So we'll do pruning without anything. Whoops. All right, we're just doing pruning. So we're doing this configuration, pruning, no caching, no sorting. If I remember correctly, this used to take like 15 seconds. But when I set this bot online, some of the moves would take over a minute, like up to 2 minutes. And so I just got a bunch of timeouts, or the bot would lose a bunch of games by running out of time. This is, or was this one 15 seconds, or was it a minute? Okay. Well, while we wait, let's stare at the code some more. So the relevant code that could be causing a problem is here. It starts here where this is the recursive call. I mean, what does it mean that it didn't do anything, that it didn't change anything to add an upper and lower bound? I'm just gonna, all right, I will give into temptation, and there's this awesome website called Programming Wiki. I forget what it's called. Chess Programming Wiki, chessprogramming.org. And in it describes, let's see if I can search for. So this is the closest to what I'm implementing. This is negated negamax reasoning. But I need to do it with alpha beta pruning. This is not alpha beta pruning. This is just standard no pruning. They don't have a link. Okay, so I guess I will search for alpha beta. Okay, so there's some. This is decently written. In fact, this was really useful. I saw this when I was browsing. That this is an estimate of how many positions you have to evaluate. If you don't do alpha beta pruning, this is how many you have to evaluate when you go to certain depths. Here, I think the way that they're defining depth, because I know the branching factor is approximately 40. They mean per moves, not per plies, or not per turns. So this is one turn. This is a second turn. This is your next turn. So at that point, you're at 64,000. A couple of turns later, you're at 102 million. I mentioned some of these numbers last stream as well. And if you're alpha beta pruning, and if you're in an ideal situation, you'll be down to this. It's still big, but compared to you got 4 billion here. Wait, sorry. Yeah, 4 billion. You get 100,000 here. It's a big difference, but that's in an ideal case. In practice, this only happens if you have perfect move order. So, okay. So I thought I saw. This is alpha beta. This is alpha beta in the standard mini max form, which, like I said earlier is annoying because you have to keep track of the max player and the min player. So they call it with minus, they call it with alpha is minus the, oh wait, is that where I'm doing something wrong? Score is greater than alpha. If score is greater than beta, then it returns. Okay, so yeah, no, I think I'm doing it. I think it's connected. It's consistent with what I was thinking. Here's the negamax form. So this should be close, very close to the logic that I'm trying to implement here. So we have, so they call alpha beta. They have alpha and beta, where alpha, I guess, can be so alpha, I think, should translate to what I'm thinking of as my best, and beta translates into opponent's best. Let's see, does that make sense if we think of it as an upper and lower bound? Not sure. I'll have to look at the if statement, so we'll get to it. So in depth left, so that's like their max depth reasoning. So they have a nice, the way that they do the pseudocode is they count down from a total target depth. And if it's at the max depth, it's a terminal node, and they run this, which is, we can talk about that later, but it's they don't actually just directly compute. They don't suggest just directly computing the score. They actually want to run a search until no moves are no pieces are hanging, which could be expensive. So I don't know if I want to do that yet, but for now, just returning the score. And then they go into the main loop. So the main loop is they call alpha beta with negative beta, negative alpha. That's like what I do, and the depth. And then if the score is greater than beta, it looks identical to what I'm doing. Score is greater than alpha, they update alpha. So if score is greater than alpha, they update alpha. I think that's what I do. So that's this, right? So, oh wait, you know what? This is not right. I have this as if the score is the best score, but I think I actually want to compare again. Oh no, well that's what this will do anyway. Yeah, this should still work. What happened? So this took 120 seconds. And it pruned this many times, but it had to see 200,000 positions. Maybe I needed to sort it to see that. I remember seeing a 15-second computation. So if I turn that one off, I'll turn. I'm skeptical about the cache because it was definitely causing some overhead. So I'll do this one. So sorting with pruning. So by the way, sorting is just sorting the moves by some estimate of how good the moves are. And alpha beta pruning works best when you find a good move early, because then you can quickly identify when a different move is not as good as the first move. So an example of this is like if you find a checkmate, like let's say you find a move that leads to that is a forced checkmate. So it's the maximum scoring position. It's the best possible move for you. As you look at other possible moves, anything where the opponent can avoid a checkmate tells you right away that move's not good enough, right? That move is not good, and you don't need to consider all the possibilities that can happen if you make that other move, because you already know you have a forced checkmate. Okay, so that was pretty fast. So this is not fast. 48 seconds. It was fast because I got distracted. I was explaining something. Okay. I don't know if this is any faster than it was before because I can't compare the two. I guess I can do a quick hack to see what it used to behave like. Okay, well, okay, since it takes a while for me to think through all this, I might as well just run this So this is with all the tricks on. I'm going to save this in my notes. Notes. So this was. Oh, I don't have to. Well, this is with implemented. Maybe pruning. Let's run this last one. So this is trying all the tricks: caching, pruning, and sorting. Yeah, previously I'd seen that the caching just added overhead because of all the dictionary lookups. It just wasn't very, it wasn't even faster at all. But the thing is, it should be faster since it's, it's not just saving a single computation, it's cutting off part of a big tree. So it should actually be faster. So that's a mystery of why, that's still a mystery why my current implementation doesn't see a benefit from caching. So if this is working, which I doubt, but if this is working, then what we're stuck with is that we actually need to sort better. All right, 44 seconds. So probably, given that there could be some random stuff happening on my laptop, that could have been just a coincidence. But okay, I guess it's slightly faster with caching. Look at these numbers, like. We had to look at 76,000 positions. Here we had to look at 57,000. This is not actually an accurate measure of how many positions we needed to look at because there were a bunch of positions that I'm not counting that we had to look at and just quickly return a value for. Here, these are the positions we actually ran the minimax function call on. So, yeah, so 1,000 times we hit the cache. Is this consistent with that table that the chess programming had? So we were looking at, I guess, let's say we, so we're at depth 4. So they're saying that it should be about 64,000 positions. Yeah, I mean, it certainly is not this depth 4. I think they meant, well, is it? I'm not really pruning down from 2 million down to this, am I? I guess I should run the I don't want to. It will take a long time. Well, I'll run it. I'll start it running and then I'll start thinking. So let's see. No tricks. So this is full minimax computation on this. Let's see if it finishes. I have to get going in a few minutes. We'll see how close we get. But in the meantime, let's think about this. So if this is the number that we're dealing with and it's taking, I mean, first off, I would think I'd be able to calculate, compute more than, this many positions in less time than 44 seconds. So there's just some optimization that needs to happen. This goes back to the discussion I talked about at the beginning about like Python being kind of a slow language, or sorry, it's not Python being slow, but it depends on how everything's implemented. But Python chess is a pure Python library, so all of its reasoning, like counting pieces, all that stuff is like for loops in Python. Those can be very slow. So it could be that that's what's happening, that we're just dealing with a slow evaluation and that we should be able to handle 57,000 evaluations really fast. But I'm not convinced. I feel like there's still something wrong with the pruning. I also know that, like, just looking at what different chess engines actually do, actually I haven't even gotten a good view of that, but I mean, a branching factor of 40, so that's the number of possible moves on average. I think I looked it up previously and it was actually closer to 43, but on average during a chess game, the number of possible moves is something around 40. That's a huge number, right? So if you want to look ahead 4 moves, you're dealing with millions already. I guess you can prune it down to thousands, but that's in ideal situations. Yeah, I don't know. So it's possible that we just need more tricks, and there are more tricks. There's lots of tricks that people have studied over the years, and we could try using that transposition table. That's the caching idea. I'm not doing any iterative deepening. It's hard to imagine that we would gain much from iterative deepening when we can't even get to depth 4. But maybe it gets us that move order sorting, like, so the thing is we're not sorting the best way. Something I didn't show you carefully at the beginning of this stream was the way I'm sorting this is just by material count. So I'm looking at all the moves that I can consider, and I'm just saying, let's sort by material count. And what that would mean, if we sort by material count, then it's probably going to pick captures first. Of course, that's the only possible explanation. All it will do is it's going to look at captures first. So with iterative deepening, what you get is that you consider more than just capturing. You consider what will happen after the capture. But you do it to depth 2, which is really fast. And then from that, you can then use that to sort as you search for depth 3. And maybe that'll help you prune depth 3 better. And then with that, you can then decide how to order things for depth 4, and so on. So maybe with that trick, I can get to a competitive bot, competitive speed-wise. Yeah, I would be hesitant to play. I mean, what did I say? It was like 40 seconds a move. Like, that's not even fast enough to. It's not even fast enough to really compete in classical time control. I could leave it up for correspondence chess, but I don't know. I can leave it at depth 3, and it's reasonably fast. Okay, so my conclusion right now, while we wait for this, is that I don't believe that it's working the way I want it to yet. I think there's still a bug, but it's entirely possible there's no bug. So I have to think about in between sessions if there's a good way for me to really test this. Like, I really want to test it to make sure I have it working correctly. That's pretty hard to do because these recursions are just really complicated. So like writing one out by hand is not easy. So comparing against what you calculate by hand is not so easy. You have to find a situation where it fails, but that's also hard. It depends on what the mistake is that it's making. I think a sign that it just didn't change the number of positions it saw when I had the old version versus this version, that suggests that something's not completely right. But I also had a hunch last time that my version would be pretty close. So it might be that the alpha beta, that ancestor idea is really rare. So, okay, yeah. So next time I'll think about what to do next. I mean, I think coming up with a better sorting using iterative deepening is a candidate. But really, what we're stuck on is just making this faster. Right? This is the right logic to sort of play chess perfectly, but because it's so slow, we can only go to a certain depth, and so that's not very good. And that depth is tiny right now. We're at depth 3. So. All right, I gotta get to work. I said I'd do this for an hour. I've done it for an hour and 10 minutes. All right, so this is never gonna finish. I don't think this is gonna take. I think this is gonna take like 10 minutes or something. But yeah, I'd play another game against the bot, but it's not interesting because it should be playing the same moves as before. It might be slightly faster, but I don't think it is faster because we saw. It was using the same. It ended up searching the same nodes as before, so it's probably the same speed. It's only able to look, to humans it looks like a move and a half, but technically it's 3 moves, right? Because it's the computer's move, the opponent's move, and then the computer's move. So it's like a move and a half. It's able to look that far ahead, which is not very good, right? Because that doesn't even understand the idea. That barely understands the idea of taking a piece back, right? Making a trade, right? So you make a trade and then you get to calculate one move after that. That's as far as it gets. Hi, Matir. Yeah, I'm sorry. I'm wrapping up the stream now. I gotta get back to work. But I'm recording these videos. They're on YouTube, so you can check them out there. And I'll try to do more soon. This is really fun. Normally this is fun for me, but right now this is really frustrating because I can't figure out why it's not working. But it's still fun. It's more fun than work. Okay, so I'll end the stream. I guess I'll report in the next stream or someplace if this number ever comes back, if this ever calculates the number here. It might never do it, but okay. All right. Thanks for visiting. Bye, everyone. That's very kind, Matir. I'll try to make things more understandable as we move on, but feel free to ask questions. All right, enjoy. Have a good day. Bye.